Good. Fresh. I thought I'll quickly. I mean, it's still not 11. I'll start. I want to say a few things about the test. Don't be surprised in the test if the questions asked are not something that you have that has been exactly spoken. Invariably, you may be asked questions for which you have to extend what you have learned. Okay, there may be some which are directly from what is taught. There may be questions which are slightly beyond. You may have to apply, think, stay calm. I mean, someone may define a new problem for you and ask you to solve it. I mean, a new problem is a problem that has not been taught, right? It's what's the right word? Many times we don't want to test people on exact their memory skills. Okay, we want to see how whether they are able to grasp what is taught, apply what is learnt, and able to convey what they apply. Right? Stay with an open mind, and if you are able to do the questions well and good, if some questions you are not able to, don't panic. There will be other questions. All right, let's continue our journey. Okay? कहाँ गया मेरा पेन? Take the blue as well. Again, we come back to our matrix multiplication code. Correct? What's happening in this matrix multiplication? Just let's have a quick look. Let us say the C array C is initialized to 0 somewhere. I haven't shown that. Okay? I equal to 0 to n, j equal to 0 to n, k equal to 0 to n, C sub ij equal to plus equal to a sub ik times b sub kj. This is the standard matrix multiplication code, right? What happens in matrix multiplication? You are taking, let's say this is the array A, this is the array B. You are taking one row of A, you are looking at one column of B, you are multiplying this plus this plus this, this plus this and so on, right? Yesterday we talked about loads, stores and all that, no? Let's spend a bit more time on that. I multiply this row with this column. After that, what do? I multiply this row with the next column. Right? So let us say this is n. N elements have to be multiplied with n elements. After I have done n elements, this n will be reused. Do you see that? After this have been, for the next column I can reuse this. Is everyone fine with it? Once I bring n elements of one row, for me to reuse, I have to wait for the second column. I have to wait for second column. Look at this way. The first guy, when it was brought to cache, how many elements would have been brought in before its reuse? How many elements would have been brought in before its reuse? Huh? I don't care, from memory to cache. I want to multiply this with this, this with this, right? So I finish one row with one column, then I start. How many elements would have been brought from memory after the first element was brought, before its reuse? This n minus 1 elements would have been brought up, and then this n elements. So I will have a reuse after 2n minus 1 loads, right? After 2n minus 1 loads. But there is also a store happening. I am doing Cij, right? So I am this times this, that will be one element of C. So that is plus 1. There is this plus 1 element of C. Okay. So there is an element of C. This is elements of A and B. What if n is large? My L1 cache, maybe few hundreds of kilobytes or few megabytes sometimes, but yeah, small size. What if my n is so large that 2n minus 1 wouldn't fit in my cache? No, there will be continuous cache misses, not spilling, cache misses. There will be continuous cache misses, right? Isn't it? Because I brought this one to cache, I did the multiplication, then I kept doing multiplication. After some time, somewhere I reached here, out of cache, throw this element away. So there are continuous cache misses. Can we do anything about it? Any thoughts? Let's break n into parts. Let us say I do. I broke this into parts of 2. And then do what? Then do what? Sorry, each column of B. So what you are suggesting is take these two elements, multiply with this guy, this guy, this guy, this guy, this guy. That way these two are reused. Correct? Okay. That's an interesting thought. Any other thoughts? Did you understand, guys, what he suggested? He said, let's take, instead of multiplying the full row with the full column, let me multiply just these two elements with two elements here. Then these two elements with these two elements. That way I can reuse cache. This can be reused from cache for these two elements. Okay. But I will be doing a full cache miss for this. Each one will be, because by the time I come back doing over all this n, this should be gone out of my cache. So for the next row these will not be able to reuse this. What you think is the right lines, instead of looking at the full row, let me look at, can I look at a part row and do something about it. Okay. Yeah. The next thing to extend is, instead of looking at a part row, can we look at a part matrix itself, right? So let's think about that. Let us say in this matrix, instead of this is 2, think of it as some k elements here and k elements here, k rows and k columns. Okay, this k element, this k submatrix, I'll multiply with 1k here. So this will multiply with this, correct? And then this will multiply with this. Then this will multiply with this. Then this will multiply with this, right? So this row, I take this submatrix, want to multiply with this submatrix. What will I do? This part has to be multiplied with column. Then this has to multiply with this. Right? Standard rules, no? I mean, okay, maybe we should have a smaller, let's write a small matrix. Okay, this is one big matrix. I divided it into 4 matrices. Okay, and now each matrix has 4 elements each, 2 by 2. Okay, so initially I had a 4 by 4 matrix. I divided, let's just focus on one of them. I divided it into 4 sub matrices, each matrix having 4 elements. Is that fine? Now let me look at the other thing here. This one also I'll divide like that. Now this 4, initially what do you want? This to be multiplied with this guy. This to be multiplied with this guy. Because you will take this row, and multiply with this column. Take this row, multiply with the second column. So what I'll do, I'll take the same thing, I'll multiply this guy with this first. So let's write it as A1, A11, B11, A12, A21, A22, B11, B12, B21, B22, B13, B14, B21, B23, B24. Okay. What do you want to multiply? You want to do A11 times B11. Correct? This row with this column plus A12 times B21. Similarly, you want to multiply this row with the second column too. A11 times B12 plus A12 times B22 plus. There is more pluses. But now I am saying let's just focus on this blue part of the submatrix. If you just multiply this matrix, what will I do? I will multiply A11 with B11 plus A12 with B21. Similarly, I can move this matrix on top of this and I will say A11 times B13. A11 times B13 plus A12 times B23 plus dot dot dot. Similarly, A11 times B14 plus A11 times B24 plus dot dot dot. We are only see this is what we would have done in the full matrix multiplication, right? Okay, गलत हो गया. A12. Yeah, thank you. So now if you look at it, I have taken this matrix, multiplied with this matrix. I got this intermediate value here. This is not the value of, pay attention, this is not the value of C11. This is giving me part value of C11. This is giving me part value of C12. This will give me part value of, these two elements will give me the part value of C13. So what I plan to do, take this matrix, submatrix, the blue matrix. These two are chosen such that they can fit in my cache. Multiply them. When I multiply, the same row, same columns are used multiple times. They are all there in the cache. Because I am using these rows again and again while I am multiplying these two matrices, I will be getting a lot of good cache performance. And once I have taken this matrix, run it over this full part, right? Because this has to go here, 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 that's it. What do you think? Do I have to ever multiply this guy with anything bottom here? No. That's very good. So it's as if I am, instead of multiplying individual elements, I am now multiplying submatrices. This matrix with this matrix, this matrix, this row will multiply with this matrix. So what we are saying, instead of looking to multiply individual elements, think to multiply submatrices. Take the first submatrix, multiply with this. Then take the second one, multiply with this. So same thing, take this guy, I'll put a question mark here, take this question mark, push it to this, take this question mark, put it to this, take this star, put it to this, take it to this. If I am able to multiply submatrices which can fit in my cache, I will have a much better cache locality. Okay? So what I am saying, instead of taking a loop like this and going over full row, full column, go submatrix at a time. Okay? Find a submatrix, do the multiply, keep the value. So this is the first value you will get of Cij. Then when you get some other terms, that will get added. Okay? Let's see the code, how it looks. I mean, it looks pretty natural, but just a minute. Yeah. Hello. Aajao bhai. सो रहे हो? अच्छा, आई एम इन द रॉन्ग विंडो. Okay. So this is what I am doing. I have this is not my fully my I loop and J loop looks scary. Yeah, my I loop. So here I want to tile 4 elements at a time. I want to eliminate 4 by 4 tile. So my I loop I'm taking 4 at a time. Just look at it, 0. The initial was 0 to n plus 1. Here it is 0 to n plus 4. J loop, it is 0 to n plus 1. It is 0 to n plus 4. Okay. Now, for each of these, for this I loop, the outer I loop, I will do I varies from II to II plus 4. J will vary from JJ to JJ plus 4. So basically what I am saying, boss, let me complete, I will take this guy. So this is my this is my target. This is my C table. This is my C table. In C table, for the first element, I need to take this guy, this whole row, multiply with this whole column. Now what I am saying is, look, I will try to reuse. Just 1 second. There is one more minor change I want to show before this. Yeah, I will. I wanted to add one more. This is a temporary state I had. I wanted to add one more. Just. Okay, I made some minor change because I realized that the K was not done. So we'll do, this will be more, so what I am doing, I did for I, okay, for J and K, for all of them, I am saying take 4, 4, right? And now just look at this loop. The inner one. The inner one says multiply this inner matrix of A with the smaller inner submatrix of B, store it in the submatrix of C. Okay. So what I am saying, I will take one submatrix of A, one submatrix of B, do the multiplication, get some temporary, some intermediate values for one submatrix of C. Do you see that when I multiply this matrix with this matrix, I will get the values of the submatrix here, not somewhere out. That's what we are exploiting here. Sorry? See, the point is, I want to multiply submatrices. Okay, just if you focus on this, how many elements am I touching? the matrix, the submatrix of A is 4 cross 4, B is 4 cross 4, C is 4 cross 4. Right? So there are total 48 elements. If 48 elements can fit in my cache, this is nice. Isn't it? I am going for 4 elements of I, 4 elements of J, sorry, 4 elements of A, 4 elements of B, 4 elements, 4 cross 4. So these 4, why am I saying 48? See? Yeah, A का कितने elements हैं? 4 cross 4, that is 16, right? B का 4 cross 4, that is 16, C का 4 cross 4. Okay. So I will have 16 elements of A, 16 elements of B and 16 elements of C in the cache. But one thing, if you look at it, initially you wanted to take a one full row, multiply with one full column. Now the order of computation has changed. Now you are doing thoda iska, these two multiplying, then you are multiplying these two, then again coming back to multiply this and this. So the order of, we are changing the order of the evaluation. I am not sure if you are able to see it. Here you take one full row, multiply with one full column. Here what you are doing, you are taking some parts of the row, multiplying with some parts of the column. Then second part, then third part. We are able to do, in this case, because the operation that is done, the order in which you are doing is not making a difference. You cannot, so this is called as loop tiling. Instead of working on individual elements, you work on tiles of elements. You are working on tiles of elements. How do we reach from here to here? How do we reach from here to here? So for this is, there are actually multiple transformations that are happening there to reach loop tiling. Let us see one by one. The first one is what we call as strip mining. Let us say I have I equal to 0, I less than n, I plus plus, some statement s. Okay? I can replace it with for II equal to 0, II less than n, II plus plus, then for I equal to II, II plus equal to 4. I equal to II, I less than minimum of II plus 4 comma n, I plus plus s. This is called as strip mining. Yesterday we talked about it, I guess, right? Did we? No? Okay, no problem. So this is called as strip mining. So in strip mining, what is happening? You take a big loop, break it into a nested loop. You break it into a nested loop. Okay, this is called as strip mining. So now let us say n is a multiple of 4. Okay, how many iterations does the inner loop go for? Max 4. Outer loop n by 4. So the total number of iterations hasn't changed. It still is same. So the computation hasn't changed. Do you see this? I mean, this is always equivalent. It never fails. We are not changing the order of evaluation also. We are not changing the order in which the statements are executed. Iteration 0 is executed first, then 1, then 2, then 3. Here also the same thing. The iterations are not reordered. Just that I am saying do it in groups. Instead of saying, hey, do 1 to 100, I say, no, can you please do first 4, then next 4, then next 4, then next 4. Okay. and instead of 4 you can have any number, first k, second k, third k, and so on, right? So this is called as strip mining. So what I did here, I did strip mining for the I loop. Okay, maybe I should show the code. It's easy to type the code. I'm lazy. I'll show the. Okay, let's see the code now. So this is my loop. Sorry, this is my target loop. To reach here, and let me get the other one. This was my initial loop. This is my initial loop, right? I will do now strip mining for loop I. Okay, what will I get? I will get this and this and so I only did strip mining of I loop. This is, as we saw it, this is equivalent. Everyone? Krishna? What's your name? Ayan. Ayan or Ayan? And you are? Arnav. Ayan, you are fine? Okay. So we did strip mining of the I loop, right? Okay. Now what we'll do? We'll strip mine the J loop. We'll strip mine the J loop. To strip mine the J loop, let me copy this guy. Let me copy this guy and let me paste it. Okay. So now what happened? The J loop is strip mined. Let me just indent the for K loop slightly inside. Okay. So I strip mined the J loop from here. No change has happened otherwise. Okay. This is also correct. Let me now strip mine the K loop. So I'll copy line 30. I'll copy line 33, I'll paste it here. Okay. Okay. So now what I did, I strip mined I loop, J loop and K loop. Okay. So this is strip mining J and K loops. Now you know what I'll do? I'll do loop interchange. Which loops I'll interchange? I'll first interchange. I interchange this 23, 22. Okay. So let me put some labels here. Let me put it as LI, LJJ, LII, LJ, LKK, just for completeness. Okay, so now I put the label. So what I'll do, I'll interchange. Which loops you think I should interchange? interchange L this LK should remain here itself. We want to push, let's pay attention, we want to push LKK, LJJ below LII, right? So LJJ and LI can interchange. So let's interchange LJJ and LI. Yesterday we saw, no, to interchange what do we need? Yesterday we found, right? We can't always interchange. To interchange, they must be independent. So here the iterations of Li and Ljj are independent, so I can interchange these two. So I'll have, अरे आजा यार, किसका फोन बज रहा है भाई? Okay, so I interchange these two, right? I interchanged. Now I got Li and Ljj next to each other. Now I want LKK to be interchanged with first Lj. Then one more twiddle, LKK comes up, right? So yesterday we saw, no, to interchange two loops, there should be no dependence across the iterations. Yeah, we'll study about dependence, how to compute dependence. If they are independent iterations, you can interchange. So when I say, okay, good, this is a good place to check. Let's say I'm talking about Li and Ljj. When I say the iterations are, when I'm interchanging this, the iterations or the body, what is the body of this thing? This whole thing of Lj, this whole thing starting from line number 22, 23, 24, 25. This whole thing is my body. I want to know if there is any dependence, is it safe to interchange them? In a sense, okay. See, let us say I have a loop L1, inside there is loop L2, and inside there is statement S. Okay, let's say L1 is on index on variable I, this is on loop on J. So this S, let's say, is depending on I and J, correct? I want to ask myself this question, if I interchange these two, previously I was executing them in certain order, first S1, S11, S12, S13, now I will do S11, then S21. Is this order changing, making any difference? This is my bad now, right? So I should put it on silent. So this, now the question is, if I interchange, instead of going row first, now I will be going, is it making a difference? Correct. In our case, there is minor difference, but we are doing only addition. Since we are doing addition, which is commutative, doing two elements, then two more, then two more, the order is still remaining the same. No, that example, yeah, we are modifying something that we were reading here. We are the CI. Okay. I take these two elements, multiply with these this column, these two elements. I just hold that value. Next I take, much later, I take these two, multiply with these two, add there. I am not changing the final value of Cij. Just that instead of computing the full value of Cij in one go, I am taking this and holding it. The temporary values. Correct. The tile size is actually, we make sure it fits within the cache. Split it into smaller submatrices so that submatrices fit in the cache. Right? We want to split it such that the submatrices of A, B and C fit in the cache. Okay. And now we want to say that, hey, when I interchange, is there any, if I do this column first and then row, can the semantics change? If the semantics are not changing, you are fine. So now, if we interchange LJJ and LI, we got this. Now I will interchange LKK with LJ and then LI. So this LKK will float up and we get this one. So to do loop tiling, it has two things happening internally. One is strip mining and then interchange. Strip mining and interchange gives us loop tiling. So if you can do interchange, you can do tiling also, because strip mining doesn't require, and it can always be done safely. But because strip mining, I am not changing the order of the iterations. Interchange, I am changing the order of the iterations. If I can do interchange, I can do tiling. Okay. But so the takeaway here are two folds. One, instead of trying to keep the full row, full column in my cache, I am trying to keep small submatrices in my cache, do the multiplication and continue. Okay? This is better cache usage. Okay. Second part, this loop tiling consists of internally two transformations, strip mining and loop interchange. Okay. This is one of the most powerful optimizations people do for getting cache benefits. Any questions on this? Yeah. Yeah. Yeah, so that you get better cache locality. Yeah. Yes. It still does, because you are trying to get the improvement on cache B, improvement in accessing of B, but still, can I reuse what I have read of A? This is helping me reuse. What you are saying is, like yesterday we saw, reduce the, when I am reading continuous elements, can I keep getting them from cache? Here this says, whatever I brought to cache once, can I reuse? So what is loop tiling helping? I am reusing the elements that are brought to cache. Okay. Okay, so that was loop tiling. Here is one more small, I'm not sure if I want to, in the interest of time, maybe I should. I will skip loop reversal. We'll talk about loop inversion. Okay. What is loop inversion? Before we talk about loop inversion, I want you to go back to your first programming lecture that you would have, course you would have taken, say of C or Java, C++, Python. Or you would have seen there are 3 different types of loops you would have read, right? For loop, while loop, do while loop. Have you ever thought why? Why do we talk about 3 different loops? While loops look so beautiful, why don't I just stick to while loop? Can I not only use while loop? You would agree that any one loop is enough, right? You don't really need all 3 loops to I mean all 3 loops have the same more or less expressive power. Why do I have 3 different loops? One could be for programmer convenience, but is there something more to that? Correct. All of us understand the difference between these 3, right? I mean, there are 3 types of loops: for loop, while loop, and do while loop. In for loop, you have an init, predicate check, update, right? And statement S. Here you only have predicate check and statement S. Here you have statement S followed by predicate check. Correct? Why do we have 3? Is one of them more efficient than the other? Excellent point. If you look at the way we, from yesterday and today, all the optimizations we are talking about are for loops. Because in a for loop, I know that the number of iterations are guaranteed itna to hoga hi. It will do so many iterations for sure, right? So I can think of unrolling without having to check after every iteration. Let's say n is multiple of 4. I don't need to check after every iteration. Hey, is it changing, right? For example, in the unrolling code we looked at in the slides, we didn't check in between, right? We just copied the body 4 times. But if it is a while loop, we have to check. If it is a while loop, we have to check after every iteration. So unrolling a for loop is far more easier and more efficient, right? Similarly, for tiling that we saw, right? Tiling a while loop, I don't know what it means, right? It's going to be a lot more painful exercise. But tiling a for loop, it's easy to do, right? ठीक है, दिया. So for loop is important. What about while and do while? Is there a difference between the two? This is common, right? In while loop, you test the condition first, do some processing, and then at the end or somewhere, you update the count. This is while loop. So do while is something similar. I am checking at the end, right? Except the fact that do while you'll definitely execute the body at least once. While loop you check and then do. Is one more efficient than the other? Do while is more efficient. Why do you say so?
Because the first iteration helps us to know what it was. I mean, maybe we can predict how many times it will.
No, but let us say this is what I want to do. I do not know the value if count is less than limit. I don't know if count is less than limit, so I need to check. So what is the equivalent of this in a do while loop? Can someone tell me? What is the equivalent of this while loop? Um, inside why inside the do? Why not outside the do? If count less than limit, do process count, count plus plus, while count less than limit. Correct? So the reason why I don't want the if inside is it will be more expensive. Now this is count checked only once and then same as the rest. So this is equivalent to the while loop. Correct? If I have to check, then I have to check. I cannot say, oh, I'll directly write the do while loop. That will be semantically incorrect. So now this is what, so here is my question. Between this and the while loop, this is one better than the other. Time? Oh, yeah, you guys think. I have an interrupt call. First programming course, you are taught multiple loops. No one asked why are we being taught multiple loops? Why? Why are we taught multiple loops? Okay, at least we have someone arguing for a while. Okay, tell me, you are saying while can be more efficient. Why? There is no implicit, right? See, if you look at the code that is generated, maybe we should look at the code generated. Python does not have a do while loop. So sad. And you'll agree with me in a minute. You can do? Correct. Both can be expressed this way. But and if you, by the way, this is the equivalent of the while loop. For the do while loop, the equivalent also we can write. Process count, count plus plus, while count less than limit, the body. So this is the equivalent of the do while loop. Both all are equivalent. The original while loop, this is the equivalent do while loop. The bottom do while loop, this is the equivalent while loop. So both are equivalent, don't worry. Okay, let us do one thing. Let's focus on just the while loop. Let's translate the while loop. Should we? If count less than limit, or rather if not count less than limit, go to end, process count plus plus, go to begin, and this is end. Agree everyone? This is the code for the while loop. Last row. Are you guys able to see what's written here? Okay. Follow what's written here? Okay. You're able to follow? Good. Now let's generate the code for this. Okay. In terms of? No, Shanti. Just give me a minute. No, it's not related to liveness. So if it were, otherwise I wouldn't have discouraged you from continuing, but yeah. So if not count less than limit, go to end. That's the if statement. Else process count plus plus, if count less than limit, go to begin. Okay, take a look. Is there any difference between the two? First of all, let's agree that this loop is same as the while loop. If you agree that while loop, this is the right code for the while loop, everyone? All of us agree that this is the code for this. Take a look. Then we can compare these two and say which is more efficient. While loop and do while loops. Which is more efficient? Oh, you don't see it yet? Which has two jumps? The do while, there is a jump here, okay, and here, okay. So, how? Did you go to here, go to here? If condition go to. Yeah, sure. Branch is a branch most of the time, but yeah. Let's count the number of such branches. Let us say the loop executes for n times. Okay. How many branches will I have here? I will check if the body executes n times and then it breaks out. So I will check, this is n plus 1 branches. How many go-tos will I have? N times. So how many branches total? 2n plus 1 branches. Okay. Wait. What happens here? This is one branch. This is only once. And then there is a branch. How many branches? If the code is executed n times, n. Voila. Which is better? While or do while? It's not a constant. If the loop is executed n times, we are saving n jumps. We are saving n jumps, boss. And that's huge. 2n plus 1. How? Go to begin. There's only one jump. This is one branch, right? Like here, this is one branch. Here, this is only one branch. There are branches, right? Cost, yeah, thoda bahut, maybe, but it still is a branch. Branch makes my life difficult. So I have total 2n plus 1 branches, n plus 1 conditional and n unconditional. Here I have n plus 1 conditional branches. ಅವಳದ ಅಷ್ಟೇ ಅಂತೆ. Okay, which is better? Do while. So not without reason they say, hey, look, you have additional types of loops. Okay, but then there are people who still like to, like you said, prefer to write a while loop, right? Then what will the compiler do internally? Convert it to a do while loop. This is called as loop inversion. This is called as loop inversion. Loop inversion reduces the number of branches, right? When I asked you which is more efficient, while or do while, how many of you had in your mind that while could be efficient or both are equal? Huh? While could be efficient because that's what we normally use, right? But yeah, internally, nah. Okay, yeah, but internally, do while can do wonders. Okay, fine. Let's look at one more. Any questions on loop inversion before we proceed further? Maybe check just with your friends. Quick neighbors time. 1 minute neighbors time for loop inversion. I'll just go back to the previous slide. Um, yeah. No, no, nothing like that. So, for loops are advantageous when you have, when you can take some of the, take advantage of the loop optimizations. After that, I would probably see for loop and while loop are very close to each other. I'll probably change it to the while and then do while. So loop inversion I'll definitely apply even for a for loop if no other thing I need to do, because the branches are less. Even for the tiled loop, right? I will change it to a do while loop at the, if
So basically, this will be applied after what?
yeah. Because at the low level, at an assembly level, I don't have any for loop. I only have if and jumps like this. Why not reduce the jumps? Yeah, sorry. Correct. Yeah, sure. Same. I think. Yeah. I mean, you start. Yeah, what you are saying is, hey, let me start from here, and then transform it to here. Yeah. In theory, it can be done. Agreed. I'm just showing, talking at a high level. This thing. Yeah. Just 1 second. He's throwing high level interrupts, non-maskable. Let's now look at one more optimization. We call it as loop distribution. What is loop distribution? I start with a loop. Let's say it has two statements, S1 and S2. Loop distribution says, look, let me divide this into two loops such that I do I equal to this something and this. The same loop distributed to two different things. Yesterday we said, hey, if I fuse, I'll save the number of branches. Here I am saying, hey, there are advantages of sometime distributing. What's the advantage? Okay. There are times when you distribute the loop, you may be able to do optimizations on the individual parts. Maybe you can do optimizations on the individual parts. We will see what those can be in a minute. But for the time being, let's assume that I want to distribute the loop. How that is useful, we will see in a minute. Loop distribution in itself is rarely used for performance gains. Okay, though it can be. Let's see where it can be. Okay, here is I'll give an example where loop distribution can be useful too. I mean, for just loop distribution itself can improve performance. Many times we use loop distribution for other things, but it's also handy. So let us say I have a loop like this. I equal to 1, I less than n or 0, y, I plus plus, sum plus equal to a sub I. Okay? And there is a big statement here S, which let's say brings in lot of elements from cache. It does lot of things. It pretty much pollutes the full, empties the cache, whatever it had. It fills in with its own required things. Okay? Let us say this does not change A or does not depend on sum. If I distribute the loop, exactly, I'll do sum plus equal to A sub I and then one more for loop. Now this guy has, I'm accessing elements of A in order, they're all coming in cache. Cache locality will take care of it. The locality, so it will fill in all the required elements in the cache. So this is much better cache locality compared to this. So basically, if I want, but different parts of the loop, if I can treat them as two different multiple loops, it can improve. I can do loop distribution. Do all of you see this can improve the cache compared to this? Now, from now till evening, I will not ask yes no question. I'll ask you how. So do you guys see that this is more efficient than this? And if so, how? First one will be a cache miss A sub 0. After that, it will keep on, because of locality, it will keep on doing the right prefetching. Right? Because the moment I am accessing A0, it will bring the cache line. When I am reaching A7, A6, A7, it says because of locality, it will start bringing the prefetching the A8, A9 and so on. Right? So this is it much better suited for cache. So loop distribution itself can be useful for loop distribution itself can be useful for performance sometime. Okay, but we have to be careful. There will be cases where you don't want to distribute. There will be cases, I'm pretty confident. Before we go further, so to distribute the loop, what we are saying, we'll take for loop here, for loop here. Is it always safe to distribute this way? Is it always safe to distribute this way? See, let's take one more example. Here I am writing to AI, reading from BI, writing to CI, reading from DI. Totally independent statements, I have done the loop distribution. I want you guys to look at, hello, I want you guys to look at this and see what is the issue with this loop. Check with your friends. I'll come to each one of your table. If I distribute, what will happen? Check, discuss with your friend, your neighbor. So in my class once, so I keep having this neighbor's time or friend's time. So once I said, hey, okay, discuss with your friend. Then one student comes and says, that guy is not my friend. So don't call it friend's time. If you are having trouble imagining it, write down the elements that are accessed in different iterations. In iteration 1, find out which elements of A are written and which elements of B are written, and similarly which elements are read. In iteration 2, what happens? And do the same thing after the distribution. Before and after distribution, check for iteration 1 and 2 which elements are read, which elements are written. Okay, let us see. In iteration 1, in iteration I equal to 1, which elements will I write? I'll be writing to A sub 1 and reading from B sub 1, and then I'll be writing to B sub 2 and reading from A sub 1. In iteration 2, I'll be writing to A sub 2, reading from B sub 2, I'll be writing to B sub 3, reading from A sub 2. All of you agree with this? iteration 1 and 2 in the undistributed loop. If you distribute, what can happen? Let us see. If you distribute, in iteration 1 of the first loop, if you distribute, you will have two loops, right? One for this loop, one for this loop. So, in iteration 1, I will be reading writing to A sub 1, reading from B sub 1. In iteration 2, I will be A2, B2. Okay, just focus on this much. And in the second loop, I would be writing to B sub 2 and B sub 3 and reading A sub 2, A sub 3. Okay? Did I miss something? This is loop 1, this is loop 2. Iteration 1 of loop 1, loop 2, loop 1. Did I miss something? This is loop 1. So I am breaking it into two parts. For the second part, I am writing to B sub A sub 1. Oh, so sorry. Oh, this one you are saying, is it? Thank you. And this should be 2. Okay, good. It's good that after 3 hours of lecture, students are still awake. Trust me, as teachers, we feel it's an achievement. Good, thank you. Now, look at what's happening. Here, in the undistributed loop, I was writing to B sub 2. This updated value is being read. If I distribute, this updation happens much later. I am reading here a old value. There is a dependence. There is a dependence so that in iteration 1 I am writing, in iteration 2 I am reading. Pay attention. In S2, let's call the second statement as S2. In S2, I am writing something in iteration 1. In iteration 2 of S1, I need it. There is one more dependence, however. I am writing here in iteration 1. I am reading it in I1. It's okay because both. अच्छा ये भी गलत है क्या? नहीं in both in the input code A1 I am reading the new A1. Here also I am getting the correct A1. So it's okay for this dependence to be split up. It is not okay for this dependence to be split up. What I am saying now, no? It's okay for this dependence to be split up, not okay for some other dependence. We will study how to specify these dependencies. What type of, there is some math involved, we will come to that. When I say this dependence, we will give it a name. Some type of dependence is, positive dependence is okay, negative dependence is not okay, we will come to that. Okay. But for the time being, this example should tell us that this B that I was expecting this value, but I am getting old value. So I cannot apply loop distribution in this case. So there is some dependence from here to here. Let me make the example slightly different. just so that you will appreciate it further. Uh, I'll change this to a I plus 1. What will happen if I change it to I plus 1? All I'm saying is this is A sub I plus 1 equal to blah and B. So in iteration 1, I'm writing to A2 and reading A1. Sorry? Yeah. I'm saying is the distribution okay or not? Still not okay? Why not? Let us see. Maybe you are right. So my code is A sub I plus 1 here. Huh? All of you can see the I plus 1 here. If you see with lot of focus, this will become I plus 1. Yeah, we'll see. So in iteration 1, I am writing to A sub 2. Okay? In iteration 0, I am writing to A sub 1. Iteration 0. Iteration 1, I am writing to A sub 2. In iteration 1, I am reading which one? A sub 0. In iteration 1, I am reading A sub 1. What happens in the distributed code? Don't look at now B. B is still bad. B is bad. Don't focus on B. Let's say this is B and this is C so that they are independent. Ignoring B, is there a dependence issues with A if I change it to I plus 1? Try. If you distribute the loop, what will happen? This A1 will be computed first. And then I will be reading the A1. यहाँ भी तो वही हो रहा है. I'm first writing to A1. See, here I am only getting the updated value. Yes or no? So in iteration 2, I will read A sub 2. Updated value only. If I distribute, I still get the updated value. Check with your friend. Check with your neighbor. If I change it to AI plus 1 and A sub I, can I distribute or not? Check with your friend or neighbor and let me know. Louder. Oh, thank you. Right. So you're right. So I plus 1 for A, it didn't make a difference because the dependence is, see, the question is, after I distribute the loop, is the dependence from S1 to S2 or S2 to S1? Pay attention. If this is I1, I plus 1, the dependence is from S1 to, I am writing in a previous iteration of S1. Maybe I should just write it and then talk. What I am saying, I am writing in a previous iteration of iteration, I am writing in S1, in a previous iteration, I am reading in S2 in a future iteration. This is one case. The second case, I'll just copy it. I'm writing in S2 in a previous iteration and reading S1 in a future iteration. Remember, I'm reading the value only in what is written only. Just that in one, I'm writing in S1 in a previous iteration and using a reading in S2 in a future iteration. When I distribute, S2s happen later. All S1s happen first, all S2s happen later. So ये चलेगा because I am reading in S2 in a future iteration. But let us say this is my situation. I am writing to S2 in a previous iteration and reading in S1 in a future iteration. When I distribute, what's happening? All S2s are happening at the end. All S1s are happening first. So these writes are not showing up in just digest this thing. Look at these two statements. This is very important. This is very important. Otherwise, I wouldn't stress so much. Focus on these two and convince yourself that when you distribute, what is happening in future, I cannot depend on that anymore. Okay, I'll get the, maybe what I'll do, I'll just get the code here so that will be easier. Can I select the code? I hope I can. Yeah, I can. That's success. So this one, I'll see, I'll just change this to Dia so that there is no headache with, we'll just focus on A now. And here we'll get back to our old B. Okay. So I want you to even ignore the rest. And similarly, okay. So this one I am writing in S1, okay, or maybe I'll change, instead of saying future, previous and I'll say writing in S1 in the current iteration or in iteration X, reading S2, I'm reading in S2 in an iteration greater than X, greater than equal to X, okay. This one says I'm writing in S2 in iteration X, I'm reading in S1 in iteration greater than equal to X, okay. If I am reading in S2 in a future iteration, what does it mean? I could have done one iteration of S1, two iterations, three iterations, all iterations, and then reading in S2, chalega. Here what's happening, I am writing in S2 in iteration X. In X plus 1 of S1 I need it. So if I execute all iterations of S1 first, I need that value of S2. So basically, if there is a dependence from S2 to S1, if there is a dependence, I am writing something in S2 that is required in S1. Pay attention. If I am writing something in S2 which is required in S1, I cannot distribute. Yes or no? I'll repeat, if I am writing something in S2, so what is S1, S2 you may ask? Let me just write that also just in case. So this is S1, this is S2. Right? So if I am writing something in S1 which is required in a later iteration of S2, chalega, right? There are other issues also where okay, let's keep to this much simplicity for the timing. So what I am saying, if S2 requires a value which was written in a previous iteration of S1, I'll still get it after distribution. Yes or no? Because in distribution, what I am saying, complete all S1 first. Okay. Here what's happening? If I do all the S1s first, none of the S1s will see the value of S2. Check with your friend, check with your friends.